Hello everybody and welcome back to the channel. It's looking like we've got about 3 more days until TikTok gets banned, which means I'm about to become a super mega chad as opposed to just a normal mega chad. And secondarily to that, I may start having to take advantage of the fact that YouTube Shorts is going to get a lot more popular. So I could make coding videos on there, but I'm thinking, I'm going to be more of like a thirst trap guy, if you know what I'm saying. Got a lot of men in India that are very interested in those apparently. So I may give that a shot shortly, but we'll do some brainstorming. Anyways, let's talk about AWS Aurora. Okay, so as I mentioned, today we're going to be talking about Aurora, which is a paper out of Amazon in 2017. Now, I will note that as I was reading this paper, there were 2 pretty egregious typos, which caused me like an hour of my life to try and think about them and figure them out. For that reason, I am extremely angry with this paper, and at the end of it, I'm going to shit on it. I don't have any right to do so because I am a noob when it comes to this stuff, but I'm still going to do so because I can. And they can't respond because this is my YouTube channel. Okay, basically the gist is Aurora is an OLTP database, which means that unlike some of the other videos that we've been doing recently on this channel, they're not focused on analytics. They're focusing on, fairly low latency transactional requests. So these are good, for actual users interacting with a service. Something like a SaaS service would be where this is really going to come into play. That being said, unlike, traditional hosted databases where you can deploy them on your own cluster and, just put them in a random data center of your own, Aurora is something that is completely native to Amazon. It's in the cloud and you can scale it up and down as you need. That being said, that's to an extent, so we'll talk about that a bit more later. So Aurora is also going to perform a separation of compute and storage. Now this is something that we're seeing a lot more in modern database/data warehouse systems, though up to this point I've really only been seeing it on data warehouse systems. So this is the first time I've seen it in an OLTP database, which makes it pretty interesting. Additionally, they're going to rely on write-ahead logging pretty significantly as the source of truth and pretty much only write the write-ahead log and derive all state from that. That's going to allow them to basically lower the amount of network I/O that they're performing, and also in order to achieve both fault tolerance and also consensus about data in the event of nodes going down or, bit flips or things like that, we're going to be using some quorums as well. So we're going to bring that all together and tie it all together, but for now let's introduce the actual problem space. So basically what we're trying to replace here, or at least what Amazon is trying to replace, is people who are basically just hosting their own MySQL instances. So what does, doing something cloud native give you as an advantage? Well, for starters, you don't have to constantly be provisioning more hardware and running that on your own. You can just go click a couple buttons on a website and now all of a sudden you have more capacity. They've noticed that at least as of 2017, and this is definitely still the case today, the cloud has many, many users because people just don't want to deal with their own data centers. It's a pain in the butt. You need to hire people to do it, and that's not easy to do. So it's a lot easier to just go to the cloud. You'll pay a little bit more money, but it is going to give you a lot more ease of life. So what they're going to do is also separate the quote-unquote compute and the storage layer in their database in order to scale the 2 independently so that people who have a lot of storage in their table but not so many users versus people who have a ton of users but not so much data to actually store can get the most responsible package for them to actually pay for. So the reason they care about doing this type of thing is in MySQL you have this concept of write amplification, right? So basically when we're writing data in normal MySQL using the InnoDB engine, you have your write-ahead log. You're not only writing to a write-ahead log, but you're also probably writing to a data page either on disk or cached in memory. You're also going to be writing some amount of metadata. I believe they said it's called FRM pages. I'm not too familiar here, but still learning myself. You're writing to the bin log or the replication log as well, which is what's responsible for taking those writes and putting them out to other replicas. And then there's also this concept of a temporary double write, where the double write is basically to ensure that you temporarily write to one data page first, and then you'll write to a second one so that if your system completely fails and either of those pages are in bad shape, you kind of use one to go ahead and repair the other. So that's known as torn pages. And so the gist is, because we have all of these writes, and some of them need to wait for the other to complete first, we get this concept of write amplification and also latency compounding, right? So for example, if from region 1 to region 2 over here, this latency is pretty long, the amount of time that it's going to take to locally replicate the data within a region is going to be pretty big. Same goes with, if this latency is big, the amount of time to go from, one hard drive to maybe the local replica in that data center is also going to be pretty big. So what Aurora chooses to do instead is basically minimize the number of writes that they're actually making, and also they want to make only one write basically in the critical path, or as few writes as possible in the critical path, and everything else outside of that, so we don't see a bunch of compounding latencies slowing everything down. Okay, so let's take a look at the actual high-level architecture of Aurora before we dive into the other components. Sometimes people say that they prefer to do something like this before jumping in deep down, so you get a whole picture of the full thing. Basically, we've got this concept of the database layer, so this is kind of the quote-unquote compute, and then we've got the storage layer, so this is the storage. Now, interestingly, unlike analytical warehouses, the storage layer is not Amazon S3, right? These are still EC2 instances, so they're effectively servers that can be scaled separately. But, they're very CPU not intensive and very much storage intensive. So they'll probably have big SSDs on each of them. And you'll note that all of these servers are kind of distributed across different AZs, which are called availability zones. So I'll explain this more in a little bit, but basically availability zones are uncorrelated failure regions. So this is going to help us remain relatively fault tolerant to things like power outages, fires, floods, to some extent, geographic disasters, but maybe a little bit less so there. So we have some database leader. Every single write in the system, even across partitions, and we'll talk about that a little bit more, is going through the leader. The leader is then creating one centralized log, and every single time that we have a write-ahead log entry, it is being written to all of these storage servers down here. And we are trying to achieve a quorum there, which we're also going to be talking about a little bit more, for a write to be considered valid. And then we've also got a bunch of read-only followers, which are themselves maintaining a cache, so that you can cache a bunch of the database data, so you don't always have to go to the storage layer. And then this is going to basically be a high level of what we're actually doing. So let's get into it some more. You may also notice that the leader itself has a cache. It can serve both reads and writes very quickly through that cache. So the first thing that we're going to talk about is this concept of quorums, right? So for any write to be durable, it needs to be on multiple different computers. And even more so, for it to really be durable, those computers need to be distributed in a way that they aren't likely to all fail together. So you can have random hardware failures, but you can also have failures like flooding and fires and, just like a building being bombed or something like that, or me going over there and being angry in a data warehouse or a literal data center and just smashing everything with a hammer. So what Amazon chooses to do is basically take every single partition of the database, so the literal data of the partition, they'll call it a segment in the paper or protection group, and what they'll do is they will basically replicate it across 3 different availability zones, where, like I said, availability zones are regions that have uncorrelated failures, and they'll have 2 replicas per region. So ultimately we'll have 6 storage servers in total, and then the quorum that we achieve in order to basically ensure that we are getting durable data here is we'll have to write to 4 of those servers. We'll have to be able to read from 3 of those storage servers. And that is going to ensure that anytime a write goes through successfully, right, the W equals 4 and the R equals 3, if we read from 3 of those nodes, we're guaranteed to at least see that write on one of the nodes because there is always an overlap of those 2 sets. Now, what using these tunable numbers in particular is going to provide us is the following. If a full availability zone goes down, we're totally fine. We can still read and we can still write like normal. We can even have 2 decorrelated hardware failures in completely different availability zones. That's fine. We can still read and we can still write like normal. We can even have a full availability zone going down and a completely uncorrelated random hardware failure at the same time, and we're still able to read data. At some point, some data is going to have to get restored, but we'll talk about that in a second. Now note that in particular, Aurora, the paper basically talks about how a lot of people like to use 3-2-2 quorums, right? Which is 3 total replicas. You need to be able to read to at least 2 of them, or read from at least 2 of them and write to at least 2 of them. They say for their sake, that's not good enough because of the concept of, correlated failures. And so they want to be able to distribute across availability zones. Okay, so Aurora introduces this concept of segments, where segments is effectively a logical partition of the database. So it could be done by hash partitioning, range partitioning, something like that. But the point is you've got all of these 10 gigabyte segments, so that, they keep them very small from the start, and if you have to split them, you can. But the idea is that all of these segments could basically just be hosted on a bunch of different storage nodes. So even though every single segment is replicated 6 times, the actual replicas that are holding each segment can be completely different. And because of that, it means that when actually making writes to all of the storage nodes, we're very unlikely to be bottlenecked because, we can scale out this storage layer as much as we want and be writing to a ton of different places. And basically all our database writing node is doing is really just forwarding all of that data to all the storage nodes, which is why it scales out very nicely. Now, basically, the reason that we have segments that are so small, or relatively small, just 10 gigabytes, is because the designers of this system are focused on this metric called median time to repair. So they have one concept of median time to failure, which is basically, how long is it after one random hardware failure that you might see another random hardware failure? And the reason we care about median time to repair is because we want it to be significantly less than that median time to failure time. So because we're using these small partitions, we know that if we're getting close to the kind of quorum limit of, our fault tolerance here, right? If a couple of nodes have gone down, we know we can repair another new node really quickly from the existing replicas. And in practice, it takes about 10 seconds. So all you have to do is basically just copy the segment over to another replica and you're good. Now you can reestablish quorum again. Cool. Let us go ahead and talk about page generation a little bit. So basically in MySQL, like we mentioned, writes are both simultaneously going to the write-ahead log and also to local pages. That is all going to be done on the same node that is handling the writes, which means that that node is also incurring a bunch of extra, CPU and I/O to deal with that write amplification. On the contrary, in Aurora, all of these pages are being generated basically asynchronously on the storage layer. Now, all these pages are just basically a conjunction of, some amount of data that's been built up plus a few new log entries as they come in. So what's nice about that is that the storage layer can basically generate this, materialized state of database pages whenever it wants. It doesn't have to do so synchronously. There's no guarantee of that. You can always just, return a page and also return the log entries that have occurred since then, or apply them and return those. So what's nice about this is, again, basically the storage layer can do this log application in the background when it's not receiving a lot of writes. So as opposed to MySQL, where we have a correlated number of log applications to pages with the number of writes, in Aurora, the storage layer is actually doing so in kind of a reverse correlated way, where it's waiting until it's idle, and then it can apply all of these log entries to its local page cache. Okay, we're going to start talking about log semantics, and then we're going to get into the weeds of this paper, which get a little bit mindfucky when you're reading it, but hopefully I can explain it a little bit better than that. So basically, thing to note is that, like I said, every single write in the system is going through one node, the quote-unquote database layer leader. And so what that means is every single write, or every single transaction, can have a sequence number associated with it, right? These are linearizable. We can order all of them because they're all going through the same place. So since it's possible that certain storage nodes can actually miss some of the writes, because we're using quorums here, right? 2 storage nodes can miss a write and a write can still be valid. Basically, what we want to do is have the storage nodes go ahead and gossip with one another to backfill the writes that they're missing. Additionally, because because there's only one node that's performing all the writes and then hearing back from the storage node, it can keep track of the state of the world as to which storage node has which write. And as a result of that, when a read comes in, rather than having to do a quorum read, that single node leader can basically say, okay, I know exactly which database or which storage node is up to date, and so I can just read from that one. We're going to have a lot of images shortly, which explain all of this a little better, hopefully. Cool. Another thing to note is that when we do writes, these are basically broken down into a bunch of mini transactions. So, if you have a bunch of unrelated writes, those are going to be separate transactions. Maybe they're going to different partitions of the database. But if they're related and perhaps, one of them needs to block another, or, it's an atomic transaction, obviously they have to be part of the same mini transaction. Cool. So basically, we have this concept of a durable point, right? So this is fairly important, and we're going to describe it a little bit more in a bit. But a durable point is basically saying across all of the partitions of the database, what is, first off, find the highest log entry where you can achieve a quorum, and then across all of those partitions, take the lowest of the highest log entries. So we're going to establish that in a minute. So that is called the durable point. So let's go ahead and visualize it, because I'm sure I explained that terribly. It's not that easy to understand from the paper, but we'll go ahead and do it. So on the left here, we've got, partition 1, it's 6 replicas. On the right, we've got partition 2, and it's 6 replicas. So let's say we've got this writer writing to partition 1, and he makes it to the leader first, and therefore the leader assigns him or his write with this ID of 101. Maybe it takes a while for that write to get to all of these replicas over here. And so in the meantime, this guy makes a completely concurrent write because they don't interfere with one another. The leader says, okay, that's fine by me. You're now transaction 102. So that is going to go ahead and go to partition 2, and it's going to be applied on 4 of the replicas. We try and apply it on all 6, but we only need to wait for 4 to respond to us. So once we get those responses from all of these replicas, we're not actually going to tell this guy that his write is complete yet. In fact, we'll only do so once that durable point has reached 102, which it hasn't yet because 101 hasn't been completely applied over here. Eventually, maybe these guys will reply. So we've got write 101 over here, we've got it over here, and we've got it over here, and we've got it over here. So now write 101 is durable to its partition. It comes back here, the leader says, oh, okay, the VDL is now 101. Right before this, it was probably going to be 99, based on the fact that, we had enough entries with higher than 99 over here. And, we had enough entries with 98 over here, so we're fine. 99 was good. We need to wait for 101 to go so that the leader can say, hey, the durable point is now 101. And then it can also say, oh, wait, 102 is already durable. So actually, it's not 101, it's 102. So the gist is that you're basically only increasing the durable point 1 entry at a time. And so even if another entry like this guy, 102, is technically persisted via a quorum to the storage layer, you have to wait for all of the writes in order to advance this durable point on the leader. So yeah, you can have all of these concurrent isolated transactions, but you're only increasing the durable point 1 at a time. You basically have to wait for 101 to finish in order to go back to the writer of 102 and say, hey, your write is now durable. Let's also talk about storage gossip within a partition. I implied that the storage nodes will do this to catch themselves up. So let's imagine we had, like a replica size of 3. So there were 3 nodes in a storage tier, even though in reality there are 6. So we've got node 1, node 2, and node 3. Basically, remember that not all of these entries are going to necessarily be one higher than the one before it because we have many partitions, right? So in this case, we've got entry 22, entry 27, and entry 30. That being said, in order for every single storage node to tell which entries it's missing, every single log entry contains a pointer to the one before it. So in this case, 27 is saying, hey, before this, I should see 22. 22 is saying, hey, before this, I shouldn't have anything. And 30 is saying, hey, before this, I should see 27. So we use these backlinks for the individual storage nodes to basically say, okay, wait a second, I'm missing this particular entry. Let me go ahead and get that. And then when it does get that, it may realize it's missing another entry, and then it'll go ahead and get that by communicating with the other storage nodes. I already touched on this one 2 slides ago, but just to hammer down the point, the idea is that a write, even if it is persisted to quorums first, does not technically get committed until every single write below it is successfully committed. So if I'm writing t equals 101 to one partition, we go to the quorum, and for whatever reason, that actually takes a while to get persisted. If there's a concurrent transaction with a higher sequence number in the log that finishes first, and the leader is even able to realize that, it's not actually going to go back to the user and say, hey, your transaction is committed until 101 is fully committed first. Another nice thing about this is that when the database leader gets a log, it's going to basically apply that log to this incoming page on disk. However, it's not going to actually show the new data from the new write until the durable point has gotten past that write, right? So the write needs to be considered durable, and being considered durable is not just being persisted in the storage layer, it's being persisted in the storage layer and every other write below it has also completed and been persisted in the storage layer. Okay, let's go ahead and talk about reads really quick. So like I mentioned, the leader has this concept of a durable point, right? So here it's going to be 100, maybe t equals 102 finishes, number 3 finishes, 4 finishes. Okay, now we can switch it to 101. Oh wait, 102 finished as well. So now we're actually at 102. So once we've reached 102, we can now show all writes that have a transaction number or a log number that's lower than 102. So now 101 and 102 become visible, and we can actually read those. So that's basically the gist here, is when we make a read to the database, it gets assigned a read point, where the read point is just the durable point of that database node at the time of the read. And then from there, the database, like I mentioned, doesn't necessarily have to do a quorum read to the storage layer, because it knows which one of the storage nodes are actually up to date, because it's been getting responses from all of them. And so it can just issue a read to that storage node in order to get the most up-to-date data. It's also the case that the database itself may have cached the page already, in which case it doesn't have to go to the storage layer at all. Now, if there are read replicas, basically what you can do is the leader and the read replicas can communicate with one another and say, okay, here's what we all think the durable point is right now. And so maybe you've got a leader here, and you've got a read replica here, and you've got a read replica here. So the leader knows that the durable point is 100. Maybe the 2 lead replicas are a little bit behind the read replicas. And so we determine, okay, at most, the smallest read that is going to be issued to the database, or the most behind read, is going to have a durable point of 99. That means that every single node in our storage layer over here that is holding all of the logs up to point 99, maybe they're holding 97, 98, 99, these guys can now be compacted, right? Because we know that no one is ever going to issue a read at this point or at this point. So we can compact those logs together and basically, ultimately create a checkpoint of the actual state of the database. And so this is basically going to be doing asynchronous checkpoint processing in the background, so that our storage, or actually our compute tier, is never doing so, and it's just happening in the background on the storage layer. Okay, finally we're going to talk about those read-only replicas a little bit more. We can basically have up to 15 of them, and as an optimization, rather than basically hearing when writes are going through from the storage tier, the read replicas are actually going to be receiving log writes directly from the leader. Now, when they do, they don't apply them instantly. I mean, they have them, they apply them to their local page buffers. However, they're not actually going to show them on reads until they get word of the durable point going up. And when the durable point goes up sufficiently high, then they can actually go ahead and show those log entries. If it doesn't, they have them there and they do nothing with them. Cool. And within a mini transaction, writes must be displayed atomically. So like I mentioned, if this is the leader right here, and this guy is read only, I feel like I made my my pencil size bigger somehow, which I don't love, but what can you do? The log entry is going to be sent here, and then eventually we're also going to get a new durable point. I keep saying VDL because that's a term they use in the paper, but I feel like durable point makes it easier to understand. We're going to get a new durable point from the leader, and then we can show those corresponding log entries. So this is eventually consistent, but in reality it is pretty fast, and they provide some metrics in the actual paper itself. The final thing that we'll talk about before my voice gives out and this video is done is recovery. So basically, 2 things need to happen when the database goes down and it comes back up. For starters, the storage nodes need to get in a good state, right? Because we could have some writes that are on disk, and perhaps they've corrupted certain pages or something like that. So for starters, what the storage nodes need to do are basically take whatever checkpoint they have of the state, take any of the read logs that they have, and they need to apply the read logs on top of the checkpoint to catch up to where they were. Secondly, the database separately, so this is the database tier, also needs to figure out what the durability point is. So what it can do is basically it can go to every single storage node, say, hey, storage node, give me your highest contiguous log number, which the storage node can figure out because of those back pointers that we discussed earlier. And then once it knows all of the highest log numbers amongst the storage tier, it can basically use those along with quorums in order to figure out the durability point. So you'll basically just count up across all of the partitions what the highest log number is, make sure that it is monotonically increasing, and then you'll have your highest durability point. Cool. The nice thing about this process is that it's completely decoupled. In a normal MySQL instance, the same component that is accepting writes and handling reads is also the one doing the recovery from the checkpoint state. And so that uses up a lot of compute. On the contrary, the storage nodes are doing this in the background, and so it allows the database to basically start accepting writes really, really quickly again, because it can just go ahead and send them over to the end of the log. All right, let's conclude this guy quickly. So, in conclusion, Aurora is a system that is trying to minimize the network I/O in a kind of, cloud-native MySQL or just general SQL database, right? Because they find that that's the bottleneck. They have all this write amplification because of how SQL databases, write to multiple different places on every single write, and they find that's the bottleneck in practice. So they want to reduce that. The way they do so is by treating the log as the source of truth and only writing logs over the network. Additionally, they use storage and compute as separate tiers, which have many nice benefits. For starters, the storage tier can basically compute all of these checkpoints in the background, and it's not going to slow down any reads or writes. Ideally, they can do so basically in a way that's actually inverse proportional to the amount of load on the system. They use quorums in order to ensure consistency of data across the system, and ensuring fault tolerance as well by spreading the actual nodes themselves across different failure zones. Finally, they're going to keep all writes, right? Every single partition, regardless of which one it is being serviced by the same leader node. They're going to keep them completely linearizable. Now, this is kind of the main issue I had with the paper, because despite it being clear that from the paper this is good enough for them, right? They can scale up really well. They get really good performance from that single leader. They find that using bigger EC2 instances actually gets them proportionally good performance, and that more connections is getting proportionally better throughput. It still feels to me like the system does kind of fall apart at this point, because when you have to rely on a bunch of ordered writes, it feels to me like you're inevitably not going to be able to support infinite scale, which is what a lot of our papers focus on. So in practice, it does seem like this guy gets used, and it's obviously clearly good enough for a lot of use cases. But I do wonder how it would work at like a Google scale or a Facebook scale. Anyways, guys, I hope you have a great weekend, and I will speak to you in the next one.